Welcome back, everyone, to the t-Statistic. We're going to go over a couple of practice problems to get you ready to perform the hypothesis testing on your own using the t-Statistic. So the first problem is going to be the same one that we started the lecture with, whether American men over the age of 35 get better sleep if they exercise regularly. Our population of interest is American men over the age of 35. Our treatment is regular exercise. This can also be labeled as our independent variable. And our dependent variable is sleep quality. Okay, so we're measuring how well people sleep, specifically men. If they exercise regularly, we've been able to recruit a group of 25 who exercise 3 times a week or more. We asked them, how well do you sleep on a scale of 1 to 7, and found a mean of 4.9 and a standard deviation of 1.1. And as I mentioned in the lecture, if you're trying to use a z-score, now what? So instead of using a z-score, we're going to use a t-statistic. Okay, can't use z, must use t. All right. So we'll go ahead and figure out what the t-statistic is for this particular example and see if we can reject our null. So remember that we must always start with our hypotheses. We have a null hypothesis, that is that there's no change in sleep quality, and that is the hypothesis that we are always testing against and trying to reject. Our alternative hypothesis in this case is an increase in sleep quality. So we're expecting that sleep quality on that scale of 1 to 7 will go up with regular exercise. Oops, trying to go forward. Now you have to set your alpha before you begin your testing. In this case, we'll set the alpha at the 0.05 level. This is the regular level that most behavioral scientists use, unless for some reason they are trying to decrease their level, their probability of committing a type 1 error, and so we'll just use the regular 0.05. Now remember, in order to calculate the t-statistic, we have to find the estimated standard error, and so I've put the equation up here again for you so that you can use the information I already gave you to figure out the standard error. One thing that you'll notice is that we actually are using variance, but I gave you standard deviation. All you have to do to find your variance is square it, square that standard deviation that I gave you, and now you have your variance. Pretty simple. So in this case, when we square our standard deviation of 1.1, we get a variance of 1.21, step 1. Now we plug that into our estimated standard error formula. So we're going to take the square root of 1.21, our variance for the sample, and divide it by the number of participants in our sample, which is 25. If you take 1.21 and divide it by 25, you get 0.0484. And when you take the square root of 0.0484, you get an estimated standard error of 0.22. Okay, so we'll use that standard error to find our t. So now you can find t using this formula here. All we need is the m that we found, which was 4.9. We're going to subtract that mean that we are estimating based on the scale that we used, which is 4, and dividing it by the standard error that we found. So now we simply plug all of our numbers into the equation, and we get a t value, or a t-statistic, of 4.091. Now, knowing your t-statistic alone does not cause joy or sadness. You must compare it to your critical t-value, right? So you need to check your t-distribution. So if you remember, what we found is that if we're using a 0.05 alpha, and we're only expecting an increase in sleep quality, so we are using a one-tailed test, and our degrees of freedom in this case is 24, n minus 1. So we have 24 over to the 0.05 column in our one-tailed test. That gives us a value of 1.711. So all we need to know is, does our t-value surpass that critical t-value? Okay, and so we go over here and we realize that it does. Our t-critical should be your t-critical is a 1.711. Our 4.091 surpasses it. And so we are in the critical region, which means now you can celebrate because we can reject the null. One thing that you'll notice is that the t-critical values are all positive. Your t can be negative. Your t is negative if you get a decrease. If you're expecting a decrease, right? So let's say I'm hypothesizing a 4. Let's say I get a 4 next to a population mean of 5. That number on the top will be negative. Okay, so your t values, your t-statistics, they can be negative. So you're always making sure that your value surpasses the critical value, either to the left tail or to the right tail, right? So if you're expecting a decrease, you're going to get a negative t. So don't be alarmed if you get a negative t. Okay, now that we have rejected our null, woohoo! Let's figure out if our effect size is small or medium or large or extra large. All right, so we'll use both measures of effect size to see if we have something worth being happy about. Okay, so remember that we have two ways to calculate effect size. The first is estimated Cohen's d. So now we're going to use our standard deviation of our sample instead of the standard deviation of our population because we don't have it. So in this case, we just take 4.9 to subtract 4. Sorry, I have a parentheses missing here. 4.9 minus 4, you divide it by 1.1, which was the standard deviation of our sample. And in this case, Cohen's d is 0.818. And if you remember what I said about magnitude, that means that this is a very large effect size. So let's see what kind of effect size we would get if we instead use R squared. So R squared has this handy dandy formula here. So instead of using means or standard deviations, we'll simply be using the t-statistic that we found as well as our degrees of freedom. So if we plug in the numbers that we got, our t was a 4.091. We're going to go ahead and square that, all right? And then we're going to square it again on the bottom, and we add our 24 degrees of freedom. So if you go ahead and do the math, we get that 4.091 squared is about 16.736. So we put that in two places in our formula. We add our degrees of freedom. It's basically about 16, almost 17, divided by about 40 to 41, which gives us an R squared of 0.411. And if you remember the magnitude for R squared, this is pretty big. This is definitely large, and in fact getting close to the very large effect size. So our effect size for Cohen's d and for R squared seem to be pretty well lined up. Some people think that R squared is a little bit more accurate than, say, the Cohen's d, but again, it's really up to the researcher which one they tend to use, and up to the journal which one they accept. Okay, so we'll go ahead and practice one more of our hypothesis testing using our t-statistic. Okay, for the next problem, we're going to look at memory. It's a very interesting subject. So let's say that you're testing whether a common memory training iPhone game actually works to improve memory or not. And I actually came up with this idea. These data are not real, but because there actually are a lot of games that are for the iPhone or for smartphones that are meant to improve your memory, but whether or not they actually do is not always super clear. So just because a game makes the claim does not mean it's true. So this is where research and hard numbers really come in. So let's say you know that a common memory test has a mean of 30 remembered items from a list of 100. So on average, people can remember 30 items from a list of 100 that they're given. You recruit 16 individuals and have them play the game, this iPhone game, at least once a day for a week, okay? At the end of the week, they remember a mean of 31.3 items with a standard deviation of 3. So this is the items they remembered from a list of 100. So the mean differences are real. There are two different means. We have a population mean of 30 and a mean of our sample of 31.3. So is that difference of 1.3 items remembered off of a list evidence of improvement of memory on this game? So you're going to run a two-tailed test of your data, and you're going to do it twice. So once, I want you to simply do a regular hypothesis test. So are your data enough to conclude that the iPhone game had a significant effect on memory if we use an alpha of 0.05? Okay, so I want you to run a hypothesis test looking at this question, and then do it one more time, but imagine that instead of having 16 people in your sample, you now have 36, okay, with the exact same mean and standard deviation, 31.3 with a standard deviation of 3, and see if now can you conclude that the game had a significant effect on memory with an alpha of 0.05. So let's see if having a different number of people in our sample actually changes the way that our hypothesis test works out. Okay, so go ahead and try it on your own and see what happens, and make sure to check back and see how I solved it. Okay, so let's go ahead and figure out whether or not we have a significant effect. So here are the numbers that we had. We had a population mean of 30, a sample mean of 31.3, a standard deviation of 3 for our sample, and we're working with 16 participants in our research study. So we always have to start with our null hypothesis. In this case, we are stating that the null would be no difference in memory between those who played the game and those who did not. And of course, our alternative is that there is a difference in memory between those who played the game and those who did not. And because we're not quite sure if it could increase or maybe even decrease memory, we're not going to make a directional hypothesis, which means that we will be conducting a two-tailed t-test. We'll set our critical value at alpha equals 0.05. So now that we've set all of that up, we just have to go ahead and do the math. So remember, because we're using a t-statistic instead of a z-score, we have to first compute the estimated standard error. Okay, so I'm not going to put up the formula for you. You have this in your notes and you have it in your formula sheet. But our standard error is this. So we just simply take our standard deviation and square it, divide it by our sample size, and then take the square root of that resulting number. So 3 squared is 9. We divide it by 16, which gives us 0.5625. We take the square root of that, which gives us an estimated standard error of 0.75. So remember, whenever you are conducting a t-test, when you're calculating a t-statistic, the first step is always calculating your estimated standard error. There's nothing that you can do until you have that number, and you'll either need your standard deviation, your variance from your sample, or even your sum of squares, right? As long as you have any of those three, you can figure out your estimated standard error. It's probably easiest if you just have your variance, but actually very few people report that. So you'll usually be working with either your standard deviation or your sum of squares. Okay, so now that you have your estimated standard error, you can find your t, right? And your t is simply the mean minus the population mean divided by that estimated standard error that we just found. Very similar to your z-score, not very different. And so once you plug in those numbers, we find a t of 1.733. But of course, that number is really meaningless. We have to compare it to the critical t value. In this case, the critical t is 2.131. And so the way that we find that, remember, is using our t distribution table. So you'll see that if we're using a two-tailed test, right, we're looking in the second row, and we have an alpha of 0.05, all we need to do to find the number is figure out our degrees of freedom. Because we have 16 participants, our degrees of freedom is 15. So it's n minus 1. So once we find that, we go over to the two-tailed 0.05 column, and we see that the critical t is 2.131. Okay, now this is not good news. Not good news for us. The t is not in the critical region. Our p is greater than 0.05. I know you can probably hear the sadness in my voice, but we failed to reject the null. So in this case, there's no evidence that the iPhone game has any effect on memory. In fact, that mean of 31.3 is effectively the same as the mean of 30. That's what that is saying, okay? So let's do this one more time with slightly different numbers. In fact, all we're going to change is one number, all right? So we're going to have, again, that population mean of 30, our sample mean of 31.3, our standard deviation of 3. But now let's say that instead of having 16 participants, we actually had 36. All right, so that's going to change things slightly. Our hypotheses are still the same. Our null is no difference. Our alternative is that there is a difference. I don't know what happened there. It got cut off, but it basically means that we will be running a two-tailed test. Again, our critical value stays the same. We have an alpha of 0.05. So now what's going to change is our standard error, right? Because our standard error is calculated using our sample size, right? So it was 16 and now it's 36. So we're going to put a slightly different number together to find our estimated standard error. And so it's actually going to look like this. Again, we take this, we square our standard deviation, this 3. We divide it by our sample size, which is now 36, and then we take the square root of that resulting number. Okay, so again, 3 squared is just 9. We keep that 36. 9 over 36 is 0.25. And the square root of 0.25 is 0.5. So our standard error, our estimated standard error went from 0.75 now to 0.5. And I want you to think about that. I want you to think about that for one quick second. Whenever we are working with standard error, right, whether it's estimated or not, we want it to be as small as we can get it. Because that means we expect less error between our mean and the true mean just because of error, right? So the smaller that we can get that error, the better, okay? So a smaller standard error and a smaller estimated standard error are both good things. We always want that estimated standard error to be small. Okay, so that's good. We have a smaller estimated standard error. So now we simply calculate our t. Again, we just take our sample mean, subtract our population mean, and we divide by that estimated standard error that we just found. Now our t is a 2.60. Now before you're like, oh, that's great, it's definitely passing the critical t that we had in that last problem, remember that our degrees of freedom have now changed because we have an n of 36. So our degrees of freedom are now 35, right? Degrees of freedom is n minus 1. So our degrees of freedom are 35, not 15. So our critical T is not the same as it was in the last problem. So let's see what our critical T would be. So let's see. We still have a two-tailed test, and we're still testing it with a 0.05 alpha level. So now all we have to do is figure out our degrees of freedom. But we run into a small problem. We have 30 and we have 40, but we don't have 35. So what are we supposed to do? Well, because this is a truncated version of the T distribution, we're going to play it safe. Okay, so what we do is find the 2 degrees of freedom that are closest to, that surround the one that we have. Okay, so we have 35, so that means 30 and 40 surround our degrees of freedom. So let's go back to the column we were looking at, right? So 0.05 at the two-tailed test, and we see that 30 has a critical T of 2.042, and 40 has a critical T of 2.021. So what we're going to do is play it safe and use the bigger T. Okay, so in this case, it's 2.042. So this ensures that for sure we have a significant effect if we find one. Okay, because if we use that 2.021, there is a slight chance that if we just barely surpass it, it actually wouldn't have surpassed it with a degrees of freedom of 35. Okay, so we're gonna, again, find the 2 degrees of freedom that surround it, so 30 and 40, and then we look at their critical T's, and we take the bigger critical T. That means we're playing it safe. All right, so let's go back to our problem. We have a critical T of 2.042. Remember, we used the degrees of freedom for 30 instead of 35 because we didn't have 35. Yay, our T is in the critical region. Are you guys happy, excited? Are y'all dancing in your chairs like I am? Okay, so in this case, we can reject the null. Okay, so nothing changed out of this except for our sample size, and I want you to think about what that means, right? So it means that when we have a larger sample size, we always have a smaller standard error. An estimated standard error that's smaller is better because we're expecting less error between our means, okay? And that means that we basically are better representing the treated population, all right? So law of large numbers, we want bigger samples, there's less error, there's less of a chance that we'll have an extreme score pulling our means one way or another. It just makes everything much more stable. Okay, so that's why these bigger sample sizes lead to smaller estimated standard errors and a higher probability of getting a significant effect. Okay, so the less error, the better, because that means our difference is more likely to be significant, if there is a significant difference. All right, so that's your practice for the t-statistic. I hope you are all very excited to have arrived to T-Town on the T-train with me. Thank you for accompanying me on this ride, and good luck computing your t-statistics and your hypothesis testing. All right. Good luck, everyone.